Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to introduce Ben Greenstein from UCLA. Ben has been very active in the SensorNet community. He has been developing a number of systems, tools. One of them that I actually aware of, familiar with a couple years back was SNAC, with Eddie Kohler. And more recently, Ben has been working on this programming toolkit for really programming the applications using basically a task library. Ben is completing his PhD work at UCLA Sense, and under the direction of Deborah Estrin and Eddie Kohler.
That's right.
And other faculties there. So with that, Ben?
Thank you. So I'll be talking about the system challenges in building tiered sensor networks. So imagine trying to build a sensor network in a city park. We would like to instrument the city park to, say, characterize noise. This could help Dick and Jane find quiet places in the park to read a book. It could also help us locate crowds, traffic jams, or even for avid bird watchers to locate birds. So this sort of infrastructure should be able to produce notifications of where it's loud and where it's quiet, and ideally also produce raw audio so we can hear why it's loud or why it's quiet. This should be an infrastructure that anyone can use, not just PhD students. So the way this would work is that a user would query the network with a cell phone. And the query would reach PC-class devices. These PC-class devices could be hardwired to lampposts along paths in the park. Throughout this talk, I'll refer to these PC-class devices as microservers. The microservers will activate battery-powered simple acoustic samplers that I'll refer to as motes that are deployed throughout the park. The motes would collect samples, maybe produce, yes?
Do you not like babies?
Well, this goes deep into my psychology. I'm having a baby soon, so. Maybe I'll answer that in more detail later. So the network will produce these small acoustic samplers will sense the environment and produce either statistics on the acoustics or the acoustics themselves. They'll produce them and transmit them to the microservers, which in turn will, on the return path, will serve simply as gateways to the user devices. What I've described is a typical tiered sensor network. But there are complications to making this a reality. First, there are acoustic complications. Quiet means different things to different users. Dick might be interested in reading a book where there are no people talking, but Jane might be interested in a place where there are no cars honking their horns. Quiet is also a relative term, relative to ambient noise conditions. And even the way we place our sensors has a dramatic effect on their response to noise. Pointing a microphone at a speaker will obviously respond differently to pointing it away from the speaker. Within these different types of noise, there are important subclasses. Excuse me. A person talking, it might be perfectly reasonable to read a book while a person's talking, but not while, to answer your question, again, a baby's screaming. A symphony in the park might be pleasant to read a book to, but not some guy next to you with a drum machine. So this points to a need for a variety of different data processing software modules. Amplitude evaluators to measure ambient noise conditions, frequency classifiers to differentiate noise sources, and specialized classifiers to detect those particularly annoying sounds, like drum machines. There are also network complications. The climate and physical variation of a deployment setting affect RF propagation. Moreover, the density of deployment will affect the available bandwidth that each node has. Densely deployed areas are more susceptible to contention and network congestion. Irrespective of these network complications, Dick and Jane should be able to get fair access concurrently to this network. Finally, there are platform complications. We have these mote class sensor nodes that we've deployed throughout the park. There are many of them. They're small and they're cheap. Unfortunately, though, they're difficult to program. They have only basic processing capabilities, minimal, very minimal storage, 4 to 10 kilobytes of RAM usually, short range, low bandwidth radios, and they run on AA batteries. At the higher tier, we have these PC class microservers that are easy to program, but they're expensive, they're large, and we have very few of them. Typically, or in our deployment, they would be welded to lampposts or maybe deployed in fields with large solar panels. But these devices, these PC class devices, can see more of the network. They're always on, they have big disks and lots of bandwidth. So ideally, we'd like to leverage the capabilities of these microservers to help the motes. So the problem is that we have these small nodes that can be widely distributed, but we somehow need to budget their communication and focus their computation in a way that allows them to still adapt to changing environments. So the problem is that we must be able to provide runtime flexibility, this sort of runtime flexibility, and still operate within the network's constraints. Put another way, we'd like to integrate the tiers and put processing where it's most needed. And I believe this is a hard problem. So at a very high level, the solution is that we need filters to process and interpret sensor data, system mechanisms to compose filters and adjust their parameters, and a system that will allow for concurrent use of these filters. And additionally, we need tools to make the execution of these filters efficient. Yes?
Is it concurrent use, or is it sort of resource allocation and arbitration? I mean, a lot of these things can be used for one thing or for another thing. We don't want to spend the battery on looking for wailing babies because we're listening for gunshots. I mean,
it's also concurrent use. I'm not sure I understand the distinction.
Concurrent use sounds like it's concurrent use. All I have to do is let everyone access the resources, right? Mm-hmm. A real sensor network seems like it's going to also have to arbitrate, access to the resource. There's going to be resource contention, and you need some kind of way of modulating who gets to use how many of the sensors, how much of the battery on the sensors, and that's very different than concurrent use.
Not the way I'm thinking about it. I'm thinking of microservers doing the arbitration on users' behalves, but then looking for ways in which, efficient ways in which we can combine tasks to execute on these on the motes. And I can get much more into that as the talk progresses. So the contributions I'll be going over the course of this talk are within the VanGo framework, in which we've developed filters for tiered systems so that we can collect high-rate data and cooperate across tiers to process that data. This is allowed for the development of new applications that require this sort of processing. A system for disseminating and controlling filters, which I'll call Tenet, where we can assemble application building blocks into tasks, and along with that comes a task execution model on motes, which includes task objects, scheduling of the objects, and managing concurrency. And finally, a planning tool that integrates tasks so in a way that evaluates network constraints. This planning tool provides language features to help plan these tasks and compiler algorithms to make them more efficient. Finally, these contributions all have practical value. They run on embedded sensing devices and PC-class microservers. So I'll begin with cross-tier cooperative filtering in the VanGo framework. So how can we build a system that's able to detect a quiet place for Dick? Conceptually, this application is pretty simple. We have a module that does the data acquisition, sense, a module that classifies that information, detect quiet, and there are various interpretations of quiet, and then a module that notifies a user. But there's a dilemma. Where do we put the quiet detector in a tiered network? We could put it on the microserver tier and collect and filter after transmission. This would allow us to collect all of the information to a safe place so that if we incorrectly filter that data, it wouldn't necessarily lead to permanent destruction of that data. However, if we put it on the mote tier and filter before transmission, we can save energy and bandwidth. So the solution of VanGo is tiered cooperative processing, which I'll argue is the best of both worlds. An application typically will have two phases, an experimentation phase and an efficiency phase. During the experimentation phase, we can collect representative waveforms to the microserver. And on the microserver can calibrate, can adjust decide which filters and what parameters we want to use for these filters to best extract the information that we need from the data set. Once we have the right set of filters and the right parameters, we can push the filters and the parameters out to the mote tier to help meet bandwidth and energy constraints. This will allow us, in particularly congested networks, allow us to return as much interesting information as possible by discarding everything else. Yes?
So this scenario of training the quiet detector on the microserver, it seems like in the scenario that you were describing, where each of us has our own definition of quiet, that you may always be in the training phase for some user, and then, well, there's always somebody who requires the mote to broadcast all the information. Yes? No? Is there a different scenario that I'm not seeing?
So can you repeat that sometimes?
Sure. I'm concerned that in the scenario that you described, because the definition of quiet varies by user, that there will always be some user within all of Central Park, who is just there trying to figure out their definition of quiet and who is forcing the system to be in the training phase. And it seems that if any user is forcing the system to be in the training phase, then you lose the efficiency for the system as a whole drops back down to the lower efficiency setting.
So two things. One, there's a limit to how many users can use this sort of deployment. And later I'll show it's probably on the order of about 50 concurrently. Second, the training phase should be hopefully much shorter than the efficiency phase during the application's execution. So yes, while any user is in a training phase, we're going to be bringing back representative waveforms and overusing our network. But that hopefully will be short-lived. Does that answer? Sort of? Okay.
Sure.
Okay. So this process is iterative. As conditions change, or if we can't tell when conditions are changing, periodically a microserver can go back to the experimentation phase and determine new filter parameters. So this is absolutely required for high-rate applications. For example, acoustics, where each node can produce lots of raw information. And best effort collection will ultimately lead to collisions and significant data loss. It's often impossible to transmit and receive all data produced. So VanGo is a framework for cooperative processing across tiers. We write filters to measure, transform, and interpret data. And these filters have consistent interfaces so that we can connect them together to serve an application's task. And filters cross platforms. So a sampler on a mote acquires data into a sample set and passes it through a filter chain. This filter chain crosses platform boundaries into a microserver. And we're able to, we connect these, a sample set passes through these filters smoothly because we're basically using message passing. So peer filters are activated and controlled by the microserver, depending on whether we want to be in this experimentation phase or this efficiency phase. So for example, if I'm trying to find the right parameters for an amplitude and frequency filters, I can activate them on the PC class device. And then when I find the right parameters, I can switch the activation over to the mote class device. So you might wonder how we go about activating these filters, and I'll discuss that in the next section. So the primary data structure is a sample set, and a sample set allows us to acquire samples in blocks. We acquire samples in blocks to reduce interrupt load and jitter. We also pre-compute the block size with respect to packet size. So for example, if we have an application that senses, then compresses that data, then sends it, and we know our packets can be no larger than 50 bytes, and our compression ratio is 4:1, then our initial buffer size in which we acquire samples into can be no larger than 200 bytes. This sort of flexibility is provided for by using attributes as our main data structure for holding and maintaining and modifying data. So an attribute is simply a tag, a length, and a value. In our system, on the motes, they're dynamically allocated and marshaled into packets. The drawback with any attribute system is overhead in maintaining these tag and length fields. So to give you an example of how this iterative tuning works, imagine a cell phone ringing in a quiet environment, and our goal is to collect the sound of the cell phone ringing. So we could collect raw samples of the cell phone ringing to a microserver and determine which filters are needed. And in a quiet environment, an amplitude classifier is probably all we need. Once we find the right threshold for this amplitude classifier, we can pass the filtering responsibilities over to the mote, activating this in-network. However, under different conditions, this time a cell phone is ringing in a noisy environment, we might have to do something different. So this time we collect raw samples to a microserver, but we realize we need more than just an amplitude classifier. The cell phone, using amplitude alone will not be able to extract the cell phone ring, the sound of the cell phone ringing. So in this case, we need, it turns out we need a convolution filter before thresholding on amplitude. So back at the microserver, we determine the correct filters and their filtering parameters, and then activate them in network. Yes?
Do you assume all these filters are already implemented on the motes?
Yes. Yeah, so I'm assuming that we have a library of filters on the motes that we can activate and assemble arbitrarily.
So what the microserver send are just parameters and who's activating?
It's who's activating, in which order, and parameters, yes. Okay. Yes?
How do the microservers know what a cell phone sounds like? Is there a training phase where a person has to say,
yeah,
here's
so for now there's user involvement.
Yeah, okay.
But that opens up a wide area of exploration. So the VanGo framework has other filters. The convolution filter is a pretty heavyweight filter for a mote. Dominant frequency filter is estimates the dominant frequency of a signal in the time domain by counting the number of zero crossings in the signal. So we can use the dominant frequency classifier to say, is the dominant frequency of a signal within some range? A spike detector can find spikes in a waveform and summarize them. ADPCM is a standard audio codec. And stats can annotate waveforms with information like the mean and standard deviation. So we've built several applications with VanGo. The first is called Oracle, and it's for acoustic acquisition and processing. So this can be used to determine if airport traffic affects local sleeping conditions, or, for example, to monitor a conference room, not just for its availability, but for its mood. Are there people yelling in the conference room? So users, this works by having users send data collection commands to Oracle motes. And users can adjust in-network filtering based on centralized processing at a microserver. So again, the challenge here is that we have too much data to collect it all, so if we must discard some of it, how can we be smart about it? So the system consists of a microserver, in this case a laptop, that communicates with a Telos B mote, which is produced by a company called Motive, which is connected to a microphone and amplifier. So Telos B has 10 kilobytes of RAM, very small considering the amount of data we can collect when acquiring acoustics, and a very slow microcontroller and no application-specific DSPs. So all of our signal processing must be handled in software. So our first hypothesis is that in-network filtering on the motes can increase the total recovered signal energy by reducing link contention. And so our goal is to collect as much signal energy as possible. Our experiment consisted of 12 sensors spaced 6 feet apart. At one end of this chain, we placed a loudspeaker and played a recording of 2 minutes of Jimmy Carter's Crisis of Confidence speech, occasionally and anachronistically interrupted by a cell phone ringing. We sampled at 4 kilohertz, which is barely sufficient to collect voice. And we ran it in 2 modes: when the sensors collect everything and when they filter on the amplitude. So in this first experiment, we look at how amplitude classification can increase the total recovered signal energy. So the y-axis is the total recovered signal energy normalized by the energy available to motes. The x-axis is the amplitude threshold that we try for a number of experiments. So for example, an amplitude threshold of 200 millivolts means any sample set that contains values that contains samples whose values are above 200 millivolts should be transmitted, and then the rest should be dropped to the floor. Otherwise, should be dropped to the floor. So this upside down V indicates that finding the right threshold for our amplitude is very much a game of matching filter aggressiveness to link availability. So to the left of this peak, we're not filtering enough before transmission. So each of our motes is trying to transmit too much data, which ultimately leads to channel contention and random loss of data, random loss of packets, including important information. To the right of this peak, we are proactively filtering too much, which leads to channel underutilization and significant feature loss. So one approach to trying to find the right operating point would just be to estimate your ambient noise and set a threshold just above ambient noise. In this experiment, our ambient noise was at this green bar at 50 millivolts. And it turns out that this iterative experimentation actually proactively cutting out some of the filter we thought we were interested, proactively cutting out some of the waveform we thought we were interested in, turns out to yield twice the energy of doing the simple approach of just filtering just above ambient noise. So in our second experiment, we add a frequency domain classifier to this mix. Yes?
So it seems like total signal energy is more of a micro benchmark than a macro benchmark. Like I don't have any intuition for 17% of total signal energy versus 25% of total signal energy being what I need in order to reliably discriminate cell phone ringing.
Right. So you're right. It's not a benchmark that's tailored to any particular application. Okay. But it was the most general way we could think about: are we capturing our signal, or the signal we're interested in? So that's a fair criticism. Yes.
Another game to play on the same axis is to change your sampling rate. Mm-hmm. Right.
Yeah.
If you're only interested in low frequency signals, you don't have to sample that fast, and that reduces everything. The amount of data collected, amount of data transmitted. So have to look into that angle.
Not yet. No.
So all these are the same sampling.
The same sampling rate. So in our second set of experiments, we use a frequency domain classifier along with an amplitude classifier. And so first of all, our first and primary hypothesis is that simple sensor nodes can discriminate classes of high-rate signals. So our goal this time is to capture as much of the cell phone signal measured in terms of total energy, independent of what we capture of the voice. So in our experiment, we collect baseline measurements. We collect recordings of Jimmy Carter and the cell phone ringing in an unconstrained environment, and then compare them to what we're able to capture in a constrained environment. So the y-axis in this graph is again the energy we were able to recover from the network, again normalized by the energy available in the network. This time, however, it's broken down into two components. The part corresponding to the Jimmy Carter's voice, and the component corresponding to the sound of a cell phone ringing. The x-axis is the minimum dominant frequency that we allowed to pass. So for example, a minimum dominant frequency of 400 means that any sample set that contains a dominant frequency that was measured to be greater than 400 hertz is transmitted. So first of all, it seems that this minimum dominant frequency discriminator discriminates well. The solid lines are the energy corresponding to the cell phone ringing. The dotted lines are the energy corresponding to Jimmy Carter speaking. And so we see at roughly 500 hertz, there's a steep drop-off in almost to zero of the energy contribution of Jimmy Carter's voice. This directly translates to a savings of energy in transmitting packets. In our recording, 37% of the time we had Jimmy Carter speaking without being interrupted. And we're effectively able to to suppress all transmissions during that period. That leads to a 55% reduction in traffic generated. Also note that amplitude classification reduces contention. Since we have so little RAM to deal with, to work with on these motes, when a mote receives, say, the sound of a cell phone ringing, it needs to transmit that almost immediately. So if our entire network hears the same cell phone ringing, then it's going to create a lot of contention. In the same way as in the last experiment, where we were able to proactively filter some of that by applying an amplitude threshold classifier, we can do the same here. So this higher horizontal line corresponds to applying an amplitude classifier above zero. Yes?
The data is timestamped?
The data is timestamped, yes. The data actually, it has a sample count in it, so there's no time synchronization protocol. So I was going to go through a second application, but I'm probably a little bit behind. The second application is called Neuromote, and it's for electrophysiological recording. And so with this application, we're able to measure spikes created by ion discharges in neurons. And so these happen about every 6 to 10 hertz, but it requires roughly 2 kilohertz to classify. And so this is an interesting problem for scientists who are interested in how these brainwaves, or how these neuron signals change as rodents interact with one another. So this is an area where we can use these motes, which are untethered devices, to acquire this sort of signal. So VanGo is the first mote framework capable of flexible high-rate sampling. So we can sample at a high rate without overwhelming the network because we have these filters, the amplitude classifier, dominant frequency classifier, and spike detector. It has iterative tuning. No filter setting is right for all environments, so we need to figure out exactly what will work. And so we can set filters interactively. And VanGo proposes this cross-tier approach where we can have experimentation and efficiency phases. So the result is that the system can find Dick a quiet place. But how hard will it be to use this? Would it take a PhD to query the system? So I'm going to talk about concurrent tasking within a Tenet architecture. So now we can detect quiet places. We can filter. We have filters for processing sensor network data, a cross-tier approach to using these filters, and we have these new applications that rely on this framework. But how can Dick activate the quiet detection and specify his preferred parameters in a way that's accessible to users? So the solution, in a nutshell, is that microservers should send tasks to motes. But this has several components. Microservers need to specify tasks. Motes need to be able to execute tasks. Microservers should be able to retask motes. And motes should be able to run several tasks concurrently. We propose a different model from TinyOS. TinyOS is the de facto standard in mote class operating systems. And our approach is tiered. We argue that microservers can be more than just gateways. And we argue for a flexible approach that can vary with user interest and environments. So we compose tasks on a microserver so application developers don't have to write any more embedded code. People like me will continue to do that. where there's lots of debugging visibility and tools for analysis, and so tasks can be composed at runtime. So for example, to create a task in which we sample every second and collect 20 samples at a time into a buffer and pass that along, we can create a new task and add 2 elements to it, periodic sampling and transmission. Once we've created this task, we can flood it to our mote network. So our tasks are comprised of a linear chain of elements to run. There are no loops or branches in our tasks, and I'll admit this is a bit aggressive, but it will lead to it does lead to simplifying the construction of tasks and to the analysis of tasks. On the motes, we take an object-oriented approach. A task is yes.
Can a task cross multiple modes, or a task only reside on a single mode device?
So no, a task is flooded to as many. It's addressed to devices, so you could address it to all devices or to a subset of devices.
But the input for task and output will be always actually constrained within the particular mode. You cannot actually say a task get data from this mode and get data from the other mode and do some collaborative processing.
Yes. So I was going to get into that. We're considering only one communication pattern, and that's from microservers to motes and from motes to microservers. So we're not allowing for any in-network collaboration among motes. If 2 neighboring motes need to communicate for whatever task that needs to be satisfied, the communication pattern would be from a mote to the microserver back down to its neighbor. Yes?
I think you're probably going to cover this later, but how does the task communicate? This is a common shared memory that all the tasks read data from it and put data back to it? Or is it like...
How do tasks communicate with each other?
Right.
They can't. So...
Okay, I'll let you go. Maybe I'll keep this question.
Okay, please. Thanks. So the task approach is object-oriented. Each task that's injected into a mote manages its own resources, parameters, state, etc. And this allows us to dynamically allocate only what's needed to execute for each task. We're not statically reserving resources. So since several tasks can be running on a sensor device at the same time, it should be up to the microserver to plan how to best make use of available resources. So here are a number of simple applications that we're able to develop using this tasking framework. So for example, to report memory usage, we inject a task that has 3 elements: wait, measure heap, and send. Wait knows how to be periodic, so this will happen periodically. To sample and send, which is probably the simplest application you can imagine a mote doing, we connect 2 elements, sample and send. This is equivalent to the TinyOS sends to RFM application. So on the mote, a task is created. A task is instantiated, and a task has a static description. In this case, there's a sense quiet task that has 3 elements: sample repeatedly every 1,000 milliseconds, channel 0, and put 20 samples at a time into a buffer. Amplitude, consider 20 samples at a time, and classify it as interesting if any value in that block is above 500. And send, which just means send it back to the microserver that sent this task. To run this task, we create an active task. And an active task has a pointer to the static description of the task, plus it maintains a bag in which it can put data as it's created and modified. So the scheduler works by looking at the elements of the task and deciding what needs to be run next. Yes?
Is this all happening at the mote?
This is all on the mote, yes. So the scheduler looks at the list of elements on the task and schedules and calls the appropriate service for each element. So in this case, the sample service knows how to interpret the parameters of the sample element and collect samples. When these samples are ready, to make sampling periodic, it's going to clone this task, add data to the current task and push it back to the scheduler. Now there's a second active task for when the next block of samples are ready. The Tenet scheduler will then see the next element on the list is amplitude. We'll pass it to an amplitude service, which might classify it as interesting, and pass it back to the scheduler. The third element is send, so we'll send it to the send service. The send service knows how to marshal the attribute bag into a packet and transmit it, and sends the active task back to the scheduler. The scheduler sees that there are no other elements on this task, so it deletes this active task. And now we have an active task sitting in sample service for when the next block of data arrives. The scheduler can handle multiple tasks at the same time. So in this case, we have a second task called send heap stats. So we use the scheduler and these services. We use the scheduler for two reasons. One, the scheduler can now interleave the elements of different tasks in an attempt to promote fairness. Also, the services don't need to know how to call the other elements in the task. They can always just hand them back to the scheduler to figure out what's next. It's pretty straightforward. So to install tasks on motes, we send a message to the mote. The only type of message that a microserver can send to a mote is one that contains a task ID and then followed by a number of elements. So in this case, we're sending the sampling task with task ID 123. And all messages are received by an installation service. So the installation service constructs a task object, calls the constructors, which are implemented by the various services, which then create the various element objects that are connected to this task. Then to activate this task, we create an active instance and pass it to the scheduler. So there are three different message interpretations in the system. When we send a task ID with a new task ID with a list of elements to execute, we're telling the mote to install this new task. If we send a task ID that's already active on the mote with element descriptions, that means modify the task. And if we send a task ID that's already active on the system with no elements, that's equivalent to it's saying replace your currently actively running task with a null task, or in other words, delete the task. So our hypothesis was that this task library would be small enough to fit on a mote and be equivalent in size to TinyOS applications. And also that we'd be able to support multiple tasks concurrently. So the task library uses about 6,500 bytes of program space and 450 bytes of RAM. The sense to RFM application, which is a TinyOS application which can sense and periodically senses and transmits, we're able to run 64 of these plus one task for collecting memory statistics all at the same time on a mote. For those of you who are interested in ROM and RAM usage, the program size to implement the entire task library plus communication stack and other drivers is only about 50% more than what it takes to just implement a single application in TinyOS. It does use about twice the RAM, but it's still well within the operating constraints of these modes. So we're able to run so many tasks because we pay for, we have very lightweight descriptions of these tasks, and we pay for each task as we use it. So example, the sense to RFM task, yes?
Does all these tasks send data from the same buffer? If say I sample something,
so no,
does all these tasks copy the data?
So it depends on how a service implements it, but usually each task maintains its own data, but it could be getting a copy of data from a shared buffer, from a buffer that's like global because it's part of the service. If that makes sense.
And this 64, I assume, is the data is actually pooled.
So 64. I'm sorry,
64 tasks.
So no, with 64 tasks, no. So each task puts 122 bytes on the heap, and that includes the data that it's collecting. So each one has its own copy of data.
That times 64 is more than...
It's under the 10K that we on Telos.
More than what you listed.
Oh, here, I'm sorry, this is statically allocated RAM. This is the heap. Yes?
So what's the comparison to TinyOS if you have, how much does a sense to RFM task on TinyOS take? I mean,
Okay, so the Sense RFM application
right.
uses 426 bytes of RAM. So we use 892 bytes of static RAM for the task library plus 122 bytes on the heap for one task.
Okay, so if I'm trying to think through what would be the Sense to RFM, the cost of running 64 instances of Sense to RFM on TinyOS, I take the RAM in the purple box under TinyOS and multiply by 64?
Yes.
Okay.
Well, but in TinyOS you can't run more than one application at once, so it wouldn't be a fair comparison.
Okay.
Yes.
This, I think, is related, but what if you had two tasks, say that one that needs to do amplitude sensing on the audio input and one needs to do frequency sensing? Mm-hmm. And so they're both going to need the microphone, they're both going to need samples. Mm-hmm. Is there any way for those two to cooperate and share that data?
Can we defer that for a few slides, because I'll address that directly.
Okay.
Okay. So with Tenet, we have this flexible, natural way of specifying tasks. So we can ask the network to detect quiet places because we've defined the elemental building blocks of tasks and a way of assembling them into chains. And it's a way of assembling these elements into chains. The network can execute tasks because we have this active task scheduling and this simple transport mechanism between tiers. Several users can do this concurrently. We can manage, because we can manage lots of tasks. They have lightweight state and we pay for it as we go. And the scheduler can interleave tasks. The result here is that Dick and Jane can query the system for quiet places. So the question is, and I think this is what you were getting at, will the queries overwhelm the network? Task planning with Snack. Okay, so now Dick can look for no baby zones. But when Jane tries additionally to look for no car zones, the network dies. There's just simply too much work for motes. So how can we fix this? So the problem is inefficient task combination. I think this is exactly your question. If we have two concurrent tasks, two sampling periods. So in this case, we have a task that's looking for babies screaming. So we're using a dominant frequency classifier. And we have a second task that's looking for just loud sounds, in this case a car honking. So we're using an amplitude classifier. If we try to run both of these tasks at the same time on a mote, this will result in interference and inefficiency. And on the motes that we work with, it's outright impossible. Even if it were possible, it would reduce sleep time and opportunities for data aggregation. So in this sense, sampling periods is a cross-task concern. Each task must be aware of the others. So the solution is task cooperation. We can have two independently specified tasks. And a microserver should be able to design one tightly integrated supertask that combines the instances of sample and combines the instances of send. The result should be a reduced ADC load and aggregated messages. Ideally, this would happen with no explicit user involvement. A constraint tool should figure out how to do this combination. So the solution is we need a task library that's friendly to this sort of combination, which I've already described in this talk. Programming language support for the development of cooperating tasks with new features that allow us to describe how tasks can cooperate. And I'll go through two, transitive connections and loose parameters. And then finally, a configuration language compiler that can weave together tasks, sharing elements as much as possible and producing an efficient supertask. So a transitive connection connects two elements in a task via some path. So tasks don't need to know about each other because they can specify their full processing paths and indicate where other tasks can be, or indicate where other tasks might weave themselves in. So for example, if we have a baby screaming task that has a sample and then dominant frequency, we can put a transitive connection between sample and dominant frequency to say that some other element could go there, just so long as sample comes before dominant frequency. In essence, what we're doing is establishing a partial order. And it's up to the compiler to resolve this into a strict ordering. The second language feature is loose parameters. A task might want one in a range of values. So for example, to detect a baby screaming, maybe our dominant frequency classifier needs to operate with a sample that's been sampled at least at 4 kilohertz. But just to measure is it loud, we might only need 2 kilohertz. So we can say the baby screaming task can operate with any sampling that's been done at least 4 kilohertz. And is it loud at any frequency at least 2 kilohertz? Yes?
So the loose parameter settings make sense to me. The other one about interweaving, could you tell me more about the intuition about why that's going to work? The reason I say that is that if I've trained my baby screaming classifier without the amplitude filter, and now you put in an amplitude filter, why should my intuition be that it's still going to classify babies?
Okay, so in this case, these are each classifiers. So they're basically looking at a waveform and marking, is it interesting?
Okay.
So all we need to do is basically OR those two together. So if this is interesting or that's interesting, transmit the sample set.
So you're saying that the amplitude doesn't do any filtering, it just annotates?
It just annotates. Well, and then at transmission, it's decided if anything has found it to be interesting, transmit.
Okay, I understand.
Okay. Sorry. So the system, so specifying parameters as inequalities creates a system of inequalities which our compiler then solves for. So in this case, with these two different sampling rates, we can a sampling rate of 4,000, exactly 4,000, will satisfy both. Finally, we have connectedness constraints. Since an active task, since we have linear chains in our tasking, we might want to constrain our elements to be connected at most once to one another. So this way we don't have a branching in our task description. So this constraint allows us to do that. And there are several other ways of specifying this constraint: at least once, any, and exactly once. So the compiler has to consider and preserve these constraints. So for example, if we have two instances of an element, x1 and x2, but x1 is specified to connect exactly once to an element y, and x2 is specified to connect exactly once to an element z, then these x1 and x2 cannot be combined into the same element in a supertask. So compilation proceeds by generating a fully specified input program, basically resolving tasks of their underlying elements, where every element reference gets a unique instance name. And then we reduce this to the minimum number of element instances, where all input element instances map to instances in the reduction, and where all input connections map to connections in the reduction. So here's an example of how the compilation proceeds. Imagine we have two tasks, sampling light and sampling temperature. In SNAC, it's pretty easy to describe this. This compiler generates the full specification. Now, this clearly is not Tenet. This is obviously not linear. SNAC was developed several years before Tenet, but we're now applying the ideas of SNAC to Tenet. So now we have this full expansion. The compiler then evaluates the constraints of the system and merges them into a minimal efficient program, or a minimal efficient supertask. So the basic algorithm of the fundamental algorithm of the compiler is exhaustive search. So if we consider the different sharings of element instances, if we just have three, A1, A2, and A3, there are 6 different ways to combine these. In general, for n instances, there's b to the n, where b is a Bell number. And this number grows quite large. So for example, in that previous application, there were 62 instances of an element called main, which corresponds to a Bell number which equal to 4 times 10 to the 62 different combinations. But it gets even worse. Since we have 20 different types in that application, we need to take the product of the Bell numbers for each element type in that application, which is some incredibly huge number, 4 times 10 to the 113th. However, since we need the smallest in total number of instances valid sharing, the first thing we can do is order our search from smallest to largest and take the first valid result. The second thing we can do is remember element subsets with no obvious problems. And when an invalid expansion is found, rather than stepping to the next expansion to test, we step to the next expansion that might address the problem. So for example, if we have two instances of a type A, A1 and A2, and we have this constraint that A1 cannot equal A2, and we arrive at an expansion where they're set to be merged together. Rather than going to any other expansion in which they're merged together, we skip to the first one in which they're not. So the result is, so in this space of 4 times 10 to the 113th expansions, by simply ordering from smallest to largest, we would find the correct result after 10 to the 36 checks. But by just applying the simple heuristic, we can find the correct result after after just 28 tests. So because SNAC combines tasks, we're hoping that our performance hypothesis is that we can have less energy consumption in transmitting messages. So what we did was compared a statically compiled application with SNAC to conventional NestC application. NestC is the programming language that TinyOS is built from. So we looked at 2 applications: the Surge application written in NestC, which can sample light and temperature and forward it to a root, and a SNAC forwarder, which is the same thing written in SNAC. We also wrote a SNAC forwarder without using the transitive connections, which will restrict opportunities, will limit opportunities to combine elements. So we looked at bytes transmitted as an indicator of energy consumed. And we ran simulations on topologies from 4 to 49 nodes. And we ran it at 100% duty cycle, which turns out to be the worst case for SNAC. SNAC can combine information from several different tasks into a single packet. And at 100% duty cycle, we have very small, the overhead in each individual packet is small. Overhead is comprised of packet header and preamble. At a much lower duty cycle on these devices, say 10%, we'd have a considerably larger preamble with one technique of low power transmission, with low duty cycle transmission. So the SNAC forwarder transmits considerably fewer bytes than Surge because it's able to merge the 2 tasks of sending temperature and sending light into a single message, and actually also merge routing control packets into the transmission of data. However, SNAC forwarder without these transitive arrows transmits about twice the data of SNAC forwarder, suggesting that these transitive arrows really do help combine tasks. So since I mentioned that SNAC was developed first, and I just wanted to give you a very quick taste of the evolution of ideas. So SNAC developed a general way of describing tasks, but VanGo and Tenet constrained tasks to linear chains. And this made them easier to understand without losing much of the flexibility. SNAC programs use attributes and message passing, and we do this also in VanGo and Tenet, but we now have refined implementations that are more expressive. So while VanGo can activate and deactivate elements at runtime, Tenet can completely reorder processing chains. So we want to create this new type of infrastructure for observing the world that's widely available and shareable, and that can support a variety of applications at the same time. The next necessary step we need to take is to deploy experimental systems. This is by far the best way to evaluate them. Specifically within these 3 projects, in VanGo, so far we've been looking at these two phases of an application, the experimentation phase and efficiency phase, where processing is either on one tier or on the other. The next step is to look at doing co-processing across tiers, coarsely processing data on motes, and then refining that processing on the microservers. Also, ideally, we'd like users to not have to ever worry about where this processing is occurring. So we'd like to implement a control system to do parameter tuning. In Tenet, ongoing work is to expand this task library. We also need tools to verify task correctness and safety. So far in our Tenet implementations, we have a single mote platform at any given time. We'd like to be able to make this more flexible, more heterogeneous. And finally, Snack was initially developed for to statically build applications, and we're in the process of turning this into a planning tool to work at runtime. So these three projects have significant related work. VanGo is not the first to consider acoustics on motes. The counter sniper system and VisualNet both do. The difference is that we're looking at creating a more flexible way of doing acoustic and other high-rate processing. We have this neuromode application, which I'm sorry I didn't have time for. Code Blue, Matt Welsh at Harvard, has similar medical applications. And all of this data processing work has its roots in internet and cellular transcoding. The difference there, though, is that where they're considering one server, many users with different requirements. In the sensor network domain, we have many servers and few users, probably many more servers than users. So Tenet differs from the standard tier approach, something like TinyDB, in two ways. One, we try to do more on the microserver tier. And two, we are not considering mote-to-mote collaboration. Tenet, you can think of Tenet tasking as a scripting language. And there's been some work in sensor networks on this. In particular, mote is a way of creating proposes a way of creating application-specific virtual machines. So Tenet you could think of as a specific instance of an application-specific virtual machine, although we're trying to be more general than the specific case of one application. And finally, Snack is built on top of NestC and TinyOS. That's our original implementation. And it has its roots in units composition models and object-oriented composition models. So in conclusion, we have this cross-tier processing that VanGo provides. We have these filters for high-rate processing. And this can support acoustics and biological monitoring applications. And it turns out that cooperating processing helps adapt to environments and save energy. In Tenet, we have this runtime. We find that runtime tasking decouples application logic from sensor devices, so that hopefully there'll be no more mote coding for application developers. And Tenet tasking provides for concurrent application support. And finally, Snack provides us with a language and compiler to create cooperating tasks, and this saves us energy. So in summary, I believe that this city park infrastructure that I began with for noise characterization is not very far away. Thanks. Sure. So questions? Yes.
I think I still don't quite understand how the tasks interact.
Okay.
It seems like they have a different approach in Snack. You try to do the static analysis and try to reuse whatever the tasks are, like the sample data and things like that.
So are you thinking of something like maybe IrisNet?
Not really. And on the other hand, your runtime in Tenet seems to assume there's a task scheduler and sort of fetch the task and run it. Every task maintains its own bag of data.
Yes.
Are these two connected, or they're sort of independent?
So what was the first of the two?
The Snack approach, the Snack way of weaving these tasks.
Okay, so the idea is that on a microserver, several tasks are specified, and if possible, they're woven together. And then if a super task that's woven together from several tasks can be injected into the mote network. And so it's maintaining the data for all of the users. So it's kind of shared among those users.
So the task you give to Tenet is already something that's woven together.
The task, No. So Tenet has two sides to it: the microserver tier and a mote tier. On the microserver tier, one of the jobs of the microserver is to figure out how to weave together several tasks.
Once we weave together and send it to the mote,
then we send it to the mote. Yes.
The mote will basically treat task as something.
As a single task, yes.
Okay. If another task comes in, the microserver will do the weaving.
Yeah. So think of it as the microserver is trying to figure out how tasks can share their data, and it will identify opportunities for sharing, and then pass it and create tasks for the motes that take advantage of that sharing.
The second task, when the microserver schedule the second, will we weave the second task?
Yes.
Would it consider what's already running on the motes and take it back?
It would have to, yes. So basically, it would be a replacement or modification of the initial task.
So there's basically no concurrency on the mote.
There's no concurrency in what sense?
You don't need multiple tasks because the microserver has already weaved everything.
No, because there could be incompatible tasks or tasks. Like, for example, one user might just want to know what temperature it is every second, another might want acoustics from that node. In which case, you could run two concurrent tasks that have really no overlap in the data that they're producing.
Okay, we'll take this offline.
Okay.
Still not finding
It seems like a microserver for runtime adaptation needs to actually monitor the execution of the tasks on the mode. And so do you actually have support for that, so that let's say some mode might actually run out of battery power, or mode may not respond as was anticipated? Does the microserver has a support to actually periodically monitor how the task is progressing and do adjustment appropriately?
So only by injecting tasks that do that monitoring. So, for example, we have this monitor heap task, so it can periodically send heap usage. Another one for periodically sending the routing table. We don't have one for measuring battery voltage, but I mean that would be straightforward. Yes.
For any of your three systems, I wonder if you can give an example of where hand coding would have worked better than what your system compiled the tasks into.
Okay, so I'll give you I'll give you the biggest pushback I've heard about Tenet, and so the Tenet model is that there's no collaboration between modes. And so there's this demonstration that Berkeley did called the Pursuer-Evader game, where there was an array of a two-dimensional array of motes and an evader robot walking around this field and a pursuer trying to track it. And it was using information generated by magnetometers on the motes to try to find this evader. And so the argument that we heard from them was that this application couldn't be done in Tenet because you need mote-to-mote communication, because you simply have too much bandwidth. You're wasting too much bandwidth by transmitting back several hops. And it's turned out not to be true. So it's less efficient the way we're doing it. So what happens is we need neighbor-to-neighbor communication. We send it back to a microserver and then down to the neighbor. But our network is bounded. 2 to 3 hops. Even in the original Pursuer-Evader game, they only considered out to 3 hops. But there are cases where you would like, particularly in data acquisition, where you would like slightly tighter, a tighter way of doing it than what you can do with tasks. So, for example, if you know that you want to select 3 different ADC channels at the same time, then if you don't code your element that knows how to capture values off the ADC well, if you don't encode it to handle several channels at the same time, then you'd have to do them sequentially, and it's less efficient. Yeah.
Another question about the reuse of these futures. How tightly are the futures assume they know the data structure in the back?
So each filter, I'll call them elements. Each element knows only about its own It knows only, so it has, basically it has a description of the data that it maintains and it can produce. And we have, so far, just one data structure for describing data, time series data. So it can take that data structure. But we need to do a lot more work on recognizing and enforcing like type checks along the way.
Well, thank you.
Thanks.